What's up guys, Zach Nicholson here, and today we'll be talking about how Einstein used integration by parts to come up with his famous mass-energy equivalence formula that we all know as E equals mc squared. So the first thing to cover is a basic integration by parts review, and if you've taken a calc class you can ignore this, but if you haven't, the formula is simply the integral of u dv is equal to u times v minus the integral of v du, which is derived from the product rule, but I won't go into that in this video. So to understand where the formula is coming from, we first got to understand special relativity. So we will compare it to classical mechanics, which is all the Newtonian laws, such as like F equals ma, kinetic energy. The problem with these is when you're dealing with very small, fast, or heavy objects, the principles start to break down. And this is what Einstein was exploring in his mass energy equivalence. So if we're comparing to classical mechanics, special relativity is just concerned with an object going super fast, specifically the speed of light. And what Einstein said was that the speed of light, regardless of the inertial reference frame, is the same. So I'm going to give a couple examples. You probably have no clue what I just said, but it'll make sense in a sec. So what is an inertial reference frame? This is what we first have to understand. So if you've taken a basic physics class, you already know what these are, you just didn't know you knew it yet. So the example that I'm going to use is off of a YouTuber's channel, Doc Schuster. Probably butchered that, but I just want to give him credit. So the example was, there is a train moving at 17 meters per second, and a person on the train throws a ball at 17 meters per second. Now, the person on the train, from his perspective, the ball is moving 17 meters per second. But then you got a guy over here standing on the ground, stationary, who sees the ball going 34 meters a second. So this is kind of the basic concept of inertial reference frames. Depending on if the motion of the observer, the motion of particle changes. However, this is not true with the speed of light. So for example, you have a flashlight up here shining this green light, and the light is moving at the speed of light because it's light. The person sees this on the ground. Now a little bit later, a spaceship zooms by, moving at 0.9 times the speed of light. Now you would think, based on the previous example here, that the light that's being the light coming out of the spaceship, which also has a flashlight attached to it, you would think that should be going 1.9 times the speed of light. This is completely incorrect, and regardless of the inertial reference frame, the speed of light is constant. Now this is what Einstein was exploring, because this raises all kinds of questions about classic Newtonian mechanics. If the speed of light is the same for every inertial reference frame, then classical Newtonian mechanics is wrong. So this classical formula for kinetic energy is 1/2 mv squared, as you saw in the previous work video that I did, if you have watched that. However, when an object approaches the speed of light, the kinetic energy is not modeled correctly by this formula, as we see in this example. So then it is necessary to employ special relativity to calculate its kinetic energy. This is called relativistic energy. Alright, so now let's get into the math. So if you've seen my previous work video about the relationship between work and kinetic energy, you'll know that by the work energy theorem, work is equal to kinetic energy. And we know from our basic calculus class that work is equal to the integral of force. What we did in the work video to show the equivalence of work and kinetic energy was substituted in ma for F by Newton's second law. What many people don't know is Newton's second law also states that F is equal to the derivative of momentum. So in this case, that's what we are substituting in for F as opposed to ma, as shown here. So now you have the derivative of momentum times dx. If you multiply this across, you get dp times dx dt, with dx dt simply being velocity. So then you get velocity times dp. And now you have to substitute in relativistic momentum since we're dealing with special relativity. What this is basically normal momentum times the Lorentz factor. And this is a whole nother topic in itself, but all you need to know really is you need to use this factor when you're dealing with particles approaching the speed of light. So all we did here was substitute in relativistic momentum for p, so now you have v times the derivative of this mess. So you'll notice this is in the form of the formula over here we know as integration by parts, u and dv. So our u in this case is v, and our dv in this case is this relativistic momentum here. So if we follow the formula, we have u, which is our v here, times dv, which is relativistic momentum, leaving us with relativistic momentum times velocity, or this shown here, minus the integral of v du, v being relativistic momentum, and du being the derivative of velocity, which is simply 1. So it's just minus the integral of relativistic momentum. So now let's write this integral in a form that is a bit easier to understand. So first we'll factor out the mass because that's a constant, and we'll leave v times this to the negative 1/2, which is the same as the square root in the denominator of what we have here, times dv. So now we're going to do a little u substitution for 1 minus v squared over c squared, as shown here, to allow us to integrate this. So here is the formula we had above on the last page, but we simply substituted in a u. And then to get your dv in terms of du, we just multiplied each side by the reciprocal to get this negative c squared over 2v. And remember, the c is a constant, so the derivative of u is really just negative 2v over c squared, because that's just a number, not a variable. So then once you have all that, you will be able to integrate. So you have the first term, remember this is from b to a, but we won't worry about that just yet, plus, and then we factor out all the constants, so we have the 2c squared and mass times the integral of u to the negative 1/2. If you integrate that, you get 2u to the 1/2, as shown here, and then the 2 from the constant we factored out and the 2 from the u substitution cancel. So now, if we substitute back in the u substitution, we have the first term plus m naught times c squared times, and this is u to the 1/2, So really it's this under a square root. So now to add these two terms together, we got to find a common denominator. So we'll multiply the second term by square root of 1 minus b squared over c squared. If we do all that, we are left with the first term times or plus the rest mass times c squared times all this, because we're multiplying the two square roots so they cancel, over the common denominator we were looking for. So if you distribute all this out, you end up getting m naught v squared plus m naught c squared minus m naught v squared over the square root of that mess, which is really m naught c squared over all that, as shown here. So now we'll go back to evaluating this now that we've already anti-differentiated and combined the two terms. So our A and our B, A is going to be our rest velocity, or 0, and B is going to be our final velocity, which is just a variable in this case. So if you plug it into the first term, remember the only variable that's really in this equation is velocity, because the rest are constants. So you have the when you plug in v to this equation, you have the same equation, and when you plug in 0, you get m naught c squared over the root of 1 minus 0, which is just m naught c squared. After all that, you get this formula, which is equal to relativistic kinetic energy. And that is how Einstein came up with his famous formula, E equals mc squared. Now, you'll notice that this doesn't really look like that formula right now, but what you gotta realize is this mass is not your rest mass as shown by m naught. It's actually your apparent mass, which actually changes based on your velocity. So this m and E equals mc squared is this whole thing right here. So what is all this saying? So if you increase your velocity, the energy will increase. If velocity is a factor of the mass, then the mass also increases. Therefore, energy is mass. Also note that as energy approaches infinity, velocity must approach the speed of light. Therefore, the velocity of any particle cannot accelerate beyond the boundary of the speed of light. That's all, guys. Thanks for watching.